everyone, and thank you for joining us today. My name is John Bryan, and I'll be going through these slides with you. I'm the VP Engineering at a company called PERM INC. PERM INC is a special core analysis and enhanced oil recovery lab based out of Calgary, Alberta. And one of the services that we offer is the analysis and interpretation of NMR data. And so today we'll be talking about using nuclear magnetic resonance, or NMR, in heavy oil systems. So let's start with a little bit of background on what is NMR and how can we use it to understand our oil systems. NMR is measuring the response of hydrogen in the presence of magnetic fields. Now, the good thing about measuring hydrogen is that oil and water, so our hydrocarbons and our water, the pore fluids that we have in oil systems, all contain hydrogen, and this is what's being measured in the NMR. The output from the NMR is two parameters, the amplitude and the relaxation time. The amplitude is related to how much fluid we have present in the sample. Remember that because NMR is telling us the signal from hydrogen, the more hydrogen or the more fluid we have, the more amplitude we will have. The relaxation time is related to either the fluid or the rock properties. And in the next few slides, we're going to step through amplitudes and relaxation times and try to get a better understanding of how we can use them to interpret our responses in heavy oil systems. So let's begin with the first part, the NMR amplitude. Like I was saying, NMR is telling you how much hydrogen is present in your system. So in the examples that we have here, this is water measured at different masses, if you can see where I'm pointing. And as we add more water to the measurement, as you double the mass or the volume of water, you double the amount of hydrogen, and the signal will double correspondingly as well. So the amount of signal is directly proportional to how much measurable hydrogen is present. And if you're dealing with any NMR machine, you can calibrate now to the signal of a known fluid like water. So you can measure your amplitude per mass or amplitude per volume of water, and you can now relate all of the measurements from different NMR systems against one another. It gets a little bit more interesting when we're trying to measure the amplitude of things like oils. When we have conventional oils or low viscosity oils, they have a very similar signal strength to water. So whether I'm measuring 2 grams of water or 2 grams of oil, I would be getting the same amount of amplitude. Where things start to change is that when the viscosities start getting higher and higher, the NMR amplitude starts to drop off. And we'll talk about this in the next few slides, but the significance is that in a heavy oil system, whenever we have viscous oil present, the signal from this oil is less than the signal from water. In other words, if we are measuring a rock containing viscous oil and water, we're going to get an output of porosity that is less than the actual porosity of the rock. This is an example of a response in a heavy oil system where we have the density porosity is the output from our sandstone density log, and the NMR porosity is the output from the NMR log. In the zone at the top, we have just water present, and here the NMR and the density porosities are tracking one another quite closely. Then as we move into the oil-bearing zone, the true porosity is shown by the blue, and the NMR porosity is consistently underestimating the porosity, and this is because of the presence of viscous oil, where the amplitude was less than the amplitude per gram of water. So in a simple sense, the output from combining density logs and NMR logs, and if you had resistivity information as well to show yourself that you were in a hydrocarbon zone, this can be used to very quickly identify where is your oil pay and where is your water above and below your heavy oil system. Now, we said before there's 2 parameters that we're getting out of every NMR measurement. The amplitude is related to the amount of hydrogen that's measurably present, and the relaxation times we said are related to the fluids and rock properties. So in the example that we have here, we've got a spectrum that contains a peak at around 1 millisecond, another peak that's around 10 milliseconds, and then we've got two slower peaks at about 100 and 1,000 milliseconds. What we would like to do is be able to figure out what the contributions of these different peaks are and how we can use them to understand what is oil and what is water. So let's start with the simplest system, which is a bulk liquid system. What happens in an NMR measurement is that we start out with the hydrogen protons all lined up in the direction of the external magnetic field lines. And then at time equals to 0 in an NMR measurement, we tip all the protons 90 degrees onto what we call the transverse plane. And the protons, when they come close to one another, they dephase and they lose their energy and they go back to their equilibrium position. And so when you have a low viscosity fluid like this blue dashed light oil here, the molecules are spaced far enough apart that they can move around for a while before they'll come into contact with each other. And when they finally do come into contact, this is when they give off their energy and they relax. The fact that the fluid is low viscosity means that the relaxation is slow and we get a long T2 value of the oil. As we go to higher and higher viscosity systems, we get faster and faster relaxation times. You can see the red, the green, and the purple in these slides here as we go to 300 centipoise to 3,000 to 100,000 centipoise. And the reason for that is that as viscosity increases, molecules become much more complex and closer together, and they will very quickly come into contact with each other, give off their energy, and go back to their equilibrium. So the more complex and interwoven the molecules are, the faster they will relax, and this is also a more viscous fluid. On the other hand, we have something like a low viscosity water. So water has a very slow bulk relaxation time because it's got a low viscosity. Its molecules are far enough apart that they can move around for a while before they contact each other. If instead we take that water and we put it into porous media, the other thing that can happen is that the molecules, instead of banging into other molecules of water, they can bang into the walls of the porous medium and give off their energy to the walls. And this is what we call surface relaxation. Now, if you are inside a large container, once again, your molecules can move around for a while before they hit the walls. If you go into smaller and smaller containers or smaller and smaller pores, they'll very quickly hit the walls, and this will cause them to give off their energy faster. So in the example that we have in this slide here, this is a slow relaxing peak. This would be water inside large pores where they have time to move around a little bit before they bang into the walls. And then as we go to faster and faster relaxation times, this is smaller and smaller pores. So what we have when we're measuring water in porous media is essentially something that's analogous to a pore body size distribution, where long T2 values are big pores and shorter T2 values are smaller and smaller pores. In unconsolidated sands, we have a variety of sand and clay materials that can be present. So again, as in this figure here, this slow relaxing peak at about 2 seconds is the signal from bulk water. Again, water, a low viscosity fluid, something that relaxes very slowly. If we take that water and we put it into sand now, we are getting now the surface relaxation of water in sand. And so the water signal relaxes much more quickly than it did as a bulk fluid, because now relaxation is controlled through surface relaxation. Now the pores in the sand are still quite large because this is just a loose, unconsolidated sand. So we get a distribution of most of our water, or most of our porosity is in these larger pores, and in this sand system we had some smaller pores present as well. Now when we have clays present, clays are even smaller particles now, and the spaces between the clays are even smaller. And so essentially we have smaller and smaller pores and faster relaxation times of water. So water, again, the relaxation times are related to the pore size distribution. And if you have slower relaxing water, this is water in sand. Faster relaxing water is water inside clays. Now, how do we put all of this together? We've got, in any oil sand measurement, we've got the NMR signal from oil, because oil contains hydrogen, and we've got the NMR signal from your connate water, which also contains hydrogen. The oil is a viscous fluid, so it's going to relax mainly through its bulk relaxation, and we'll see this in the next couple of slides as well. The low viscosity water will relax mainly through surface relaxation. And so what we have then is bulk relaxation of the oil related to the viscosity, surface relaxation of the water related to the pore size distribution. If we can properly separate the signals of oil and water, now we can know two things. We can know, first of all, how much water is present, so the water saturation and the oil saturation, and we can also determine the properties of the oil, the viscosity of the oil, based on its bulk relaxation properties. So let's look at the prediction of oil viscosity. This figure makes sense based on what we've been talking about. As we go to higher and higher viscosity oils, we see faster and faster bulk relaxation, and correspondingly the T2 drops in the oil. Now, you can see as we start getting above 10,000 milliseconds, the shape of the curve starts to deviate from linearity. So we start seeing smaller and smaller changes in the oil relaxation with bigger and bigger change in viscosity. What's happening at this part of the spectrum, for these types of very high viscosity oils, is that the oils are relaxing too quickly to be measured. So they're relaxing so fast that they are outside the range of what the NMR tool can capture, and the NMR is only measuring a part of the oil signal. And so whatever the NMR is capturing, this is related to the hardware limitations, and this is why we lose this linearity between T2 and viscosity for high viscosity fluids. And most of the oil is now relaxing too quickly to be measured. The good thing, though, is that we're not only measuring the viscosity of the oil, we're also measuring its amplitude index, or its amplitude per gram. And what we're plotting here is what we call the normalized amplitude index, or the relative hydrogen index, which is the amplitude index of oil divided by the known constant amplitude index of water. So again, when we're at low viscosity fluids, the RHI is approximately equal to 1. The signal from oil and the signal from water are very similar. As we get to higher and higher viscosity systems, remember we said now the oil was relaxing so quickly that it's too fast to be measured? Well, because of that now, we will also be seeing a smaller and smaller amplitude per unit mass of oil. And so there's this relationship between RHI and viscosity as well. So if we go back to the last slide, when we go to high viscosity systems, we lose the significance between viscosity and T2GM. We lose this correlation because the oil is relaxing too quickly to be measured. But in this range of high viscosities, we can still see a relationship between viscosity and RHI. So both of these terms become very significant in different ranges of viscosity. For low viscosities, the T2 is very important. For high viscosities, the RHI is very important. What we can do is put these two terms together into a single viscosity model, which relates viscosity both to the RHI and the T2GM. And you can see the form of this model. When T2GM, when we have a low viscosity oil, RHI is going to be 1, so this term is negligible, and viscosity and T2 are inversely related, as we expect. When we get to high viscosity systems, the T2 is going to become essentially constant, and viscosity is inversely related to RHI, which is also what we saw in the last slide. So a model like this, or there are derivation or different variations, in the literature. So you can check out. There's many good sources, and if anybody ever wants to contact me, I'd be happy to pass along references to you. But there's a lot of very interesting heavy oil viscosity models that are present in the literature. Now, what we would like to do is be able to predict viscosity inside the porous media. So not just as a bulk liquid, but how can you predict in situ viscosity during something like a logging tool characterization of your oil sand system. So essentially what we would like to do is use this bulk oil viscosity model to measure viscosity if you're in situ fluids. In order to do that, we again need to be able to first separate the oil and the water. And once we can know what's the signal of oil and what's the signal of water, we can look at the oil contribution to get its viscosity. So we want to be able to measure its T2GM, and we want to be able to measure its RHI. This is an example spectrum of an oil sand. So it's an unconsolidated system containing heavy oil and connate water. And what we had done here was in the lab, we had measured the signal from the oil sand, and then we used a centrifuge to extract some of the heavy oil, and we measured the NMR signal of that heavy oil as well. So the solid blue line is the NMR of the oil sand, which contains oil and connate water signals. And then once we extracted the oil, this is this gray dashed line. Now, if you look at this slide, you can see that the first peak of that oil sand spectrum corresponds very well with that bulk oil signal. And this is as expected. This shows us that the oil is so viscous that even within the porous medium, its viscosity is controlled by bulk relaxation, or controlled by its viscosity. Sorry, its relaxation is controlled by bulk relaxation, or by the viscosity of the oil. And so essentially what we have is the bulk and the in situ T2GM values are going to be very close. And the other thing we can see is that any of this signal that's beyond the first peak can't be the contribution of oil anymore, because even as a bulk liquid, oil was relaxing very quickly. So this is the signal from connate water in the sample. So basically what we have here is a way of understanding the in situ T2GM of the oil, and a way of extracting the water amplitudes or the water saturations in the sample. This was a case study that we did a few years ago looking at a CHOPS, so a heavy oil primary production type of system. And this was looking again at predicting viscosities. And just like we saw in the previous slide, we had the ore or the oil sand material. This is the NMR spectrum of the oil sand containing connate water and heavy oil. And then we extracted some oil, and this is the gray lines in these figures. And what we are calling deconvoluted oil is just our attempt to say, well, this is the first peak of the spectrum, and you can see how well it lines up with the signal of the extracted oil. So the conclusion is that the mean relaxation time of the first peak matches with the mean relaxation time of the bulk oil, or that the oil is so viscous that if we can take that first peak to be the signal of oil, we can now use that to get the T2GM of oil for our viscosity correlation. Now remember that we had two things we needed to predict viscosity. We had T2GM, which we got directly, and then we had RHI. RHI is more difficult for an in situ fluid because in order to get the amplitude per gram of oil, you need to know how much oil is present. And this is an unknown in an oil sand system. Fortunately, because what we were looking at previously is that there's always this relationship between RHI and viscosity and between T2GM and viscosity, if you're in the range where T2GM is changing with viscosity, then there will also be a relationship between RHI and T2GM. And so if now we take RHI as a function of T2GM, so we can get from the oil sand spectrum, the measured geometric mean relaxation of the oil, we can calculate RHI as some function of this, and what we are left with is a nonlinear correlation between viscosity and T2GM. How did this work? Well, here's for this same case study, the blue points are extracted oils where we measured the viscosity in the lab, and the dashed triangles are the predicted NMR viscosities that we made from core. So blue is measured bulk oil viscosity, and these triangles are the predicted in situ NMR viscosity. And you can see here that we were able to nicely capture variations in saturation, or sorry, in viscosity with depth in this system. Now, there will be cases where we go either to more viscous bitumens or even under logging tool systems, we can use the response of other logs to help us as well, and specifically the density log. The nice thing about the density log is that if we trust this log, it's giving us the total porosity of the system. And so if we know the system has a certain total porosity, and we are able to separate the first peak is oil and all the rest of the signal is water, now we can say the water saturation is the NMR water signal divided by the total porosity. Now, that total pore space should have been filled with oil and water. The water, I'm measuring properly. This is my water saturation. The oil, 1 minus water saturation. The oil, I should have been measuring a large signal from oil, but because the oil was viscous, I'm measuring only a portion of that oil signal. So the RHI is the measured oil amplitude divided by what the oil amplitude should have been in order to match the saturations of the system. So by having access to an independent measurement of the total porosity, which is your density log, we no longer need to get RHI from an RHI T2GM correlation, but we can instead predict it directly by knowing the total porosity and the water saturation. So this was another case study that we had done a few years ago. And in this case study here, this was a bitumen formation. So it was a much more viscous oil. And we were at the range where we had become very insensitive to oil T2 changes with viscosity because the viscosities were just too high for the oil to be measured. In track 3 here, what we're plotting is the density porosities from the log, and these round black points are core porosities, and you can see here that the density porosity and the core porosities track one another very closely. The NMR was predicting significantly lower porosities, the space between them being this green, and that's because the oil was viscous. The NMR was only measuring the part of the oil that was able to be measured, and so the signal strength from oil was less. So we were underestimating porosity. This was our evidence that we were in an oil-bearing zone. Now, by taking the first peak equal to oil and all the signal after the first peak equal to water, we were able to split water and oil. And water saturation is the NMR water divided by the total porosity from the density log. And that's this track here in blue, shown in track 4. And these points are the Dean-Stark water saturations. And you can see that the NMR and the Dean-Stark water saturations track one another very closely. At that point now, we had T2 that you could measure from the oil signal, and for this specific case study, there was very little change in T2. The viscosity was very much controlled by the RHI, but the RHI we were able to measure directly, like we had seen on the last slide. And so what you're seeing here in track number 6 is the measured oil viscosity points, and the red solid line is the NMR predicted in situ oil viscosity. And again, you can see that the NMR is capturing variations in viscosity within the formation. So that's an introduction to how do we use NMR to interpret signals in heavy oil systems. I hope it was useful, and I would love to hear feedback if you guys have questions or comments or you'd like to learn more. We do offer 2-day courses on NMR and other topics, enhanced oil recovery and reservoir petrophysics. The courses are taught here in Calgary in our PERM INC lab, or if you have enough people within your company that are interested in taking the course, we'd be happy to do custom courses in your shop as well, and that will save you the hassle of coming over to PERM. We can also, of course, do NMR consulting and lab testing. We do a lot of calibration studies where we'll run tests in the lab to help to calibrate NMR logging tools, and of course any other help that you would want in terms of interpreting your NMR data, we would be happy to hear from you as well. So thank you very much for taking the time today. Hopefully this was useful and instructive to you, and as always, have a great day.